Casey, thank you very much. I also want to thank Tori Johnson and Commissioner Sly for putting this on, and I hope that this is the first of a number of conferences of this sort. I found it very useful in my area and appreciate the efforts that have gone into it. What I'm going to talk to you about today is the use of biodiesel to power a fuel cell. And I hope to convince you of a couple of things. First of all, that this is a logical way of utilizing the energy inherent in certain types of biomass, and that the catalysts that we've looked at for a key part of that transformation process are absolutely critical to the success of that energy cycle. So what I'm going to talk about today is what I've shown here on the board. We're going to take biodiesel, which I will characterize for you. We're going to spend most of our time today talking about what goes on in this reformer section. That's where the catalysts are essential. We're going to take that syngas, and I'm going to show you some results where we produce a gas called syngas, primarily consisting of CO and hydrogen, and run a solid oxide fuel cell. If you look at the overall energy cycle from the biodiesel through the electricity produced by the solid oxide fuel cell, there are some advantages that may not be apparent on the face of it. For example, there is a lack of NOx emissions that are associated with combustion processes. The solid oxide fuel cell is a very efficient way of transforming the chemical energy in the syngas into electrical energy. Among other applications for this sort of energy cycle are those that I've shown down at the bottom: military, stationary, and transportation. One example that I've become aware of recently is in long-haul truck stops. When those trucks stop for the night, they often idle their engines at what amounts to a net efficiency of about 5%. That is coupled with the emissions of NOx and other things that come out of the tailpipe during that cycle. I've read that there are commercial interests in developing solid oxide fuel-based systems where the diesel fuel, instead of being burned in the engine in the individual truck, is transformed in the cycle that I've shown you before. A small solid oxide fuel cell is used to provide electricity to cool the cabin and the trailers in that situation. In a military situation, this can also be critical. I was told that when an army moves into the field, about 70% of the weight that has to be transported to the front is fuel. Anything that can be done to improve the efficiency in generating electrical power for those military systems reduces that logistical burden, and the military has expressed an interest in this sort of fuel cycle for the same reasons. So what we're going to do today is focus on the reformer, as I mentioned earlier, but I'm also going to show you some results of tests that we've made on an actual solid oxide fuel cell a bit later. So what we're doing in making biodiesel, this is familiar to most of you in the audience, I'm sure, but we're taking the triglycerides, esterifying them in an acidic media, which also uses either a heterogeneous or homogeneous catalyst typically, to make the biodiesel and glycerol. What we're going to focus on today is the use of the biodiesel in this energy cycle. So what happens in the reformer? What we do there is we take the biodiesel that's produced in the step that I showed you a moment ago, and we react it at very, very high temperatures in the presence of oxygen and or steam to produce what's called synthesis gas. That synthesis gas consists primarily of CO and hydrogen, but also has other components, usually equilibrium concentrations of CO2 and steam as well, and those do play a part. But the problem here is that I'm going to show you in a moment that the challenges in making a catalyst that can handle these conditions is an extremely demanding one, and that's where we're going to spend most of our talk today. Now, in that arrow that I've shown you there where we take and react the biodiesel with oxygen and or steam, there are a couple of things that can happen. We can run this at a condition where we only add oxygen. That's called partial oxidation. So we take the diesel fuel, partially oxidize it to a stream consisting primarily of CO and hydrogen. That's an extremely exothermic process, and it's one that has some benefits. For example, it's kinetically much faster than some of the others. We can carry out a corresponding reaction in which instead of oxygen as the oxidizer, we use steam. That produces also a syngas of somewhat different composition, but that's an extremely endothermic reaction. If you take the two of those and carry them out in a way where you add both oxygen and steam, you can run it near autothermal conditions and produce a syngas of somewhat different composition. What we're going to talk about today, I'm actually going to show you some results in both partial oxidation and oxidative steam reforming. They both have advantages, and we'll look at results from both. So the challenge for the catalyst is that the conditions under which we carry out this reforming reaction are extremely demanding. The temperatures that I showed you before in the 900 to 1100 degrees C range in the reformer, moderate pressures and very, very high space velocities. The high space velocities correspond then to small reactor volumes. We want to reduce the size and weight of the reactor, the demands of how much catalyst is required, and one way to do that is develop an active catalyst. The challenge here is deactivation. I'm going to show you in a moment the ways in which some of these catalysts deactivate, because we've spent a great deal of time trying to overcome those challenges. But carbon deposition is one specific mechanism by which these catalysts deactivate that's especially important in these systems. So the catalysts that we develop must be thermally stable. Temperatures of 1,000 degrees C are extremely rare in catalytic processes, and most of the conventional catalysts, the way that they're prepared, will not tolerate that temperature for very long. Another thing that we've looked at is that the group AB metals have the properties that we're interested in, specifically rhodium. It has the ability to activate the molecules that we're interested in and retain some of its active properties in the presence of these demanding conditions. However, traditional supported metal catalysts simply do not work at these conditions. Most of the catalysts that are used in industry and are made up of metals such as this that are supported on an oxide support. One of the ways that these catalysts deactivate at these high temperatures is that these supported metal crystals become mobile at the temperatures that we're interested in for reforming. They migrate from either atomically or as crystallines to form larger crystals, shown here on the right, and that particle size growth results in, at the very least, a loss of active surface area, and at most, the loss of activity due to changes in the way the crystal restructures itself during this process. Another way in which these catalysts collapse at the conditions that we're interested in here is support collapse. I showed you a moment ago the oxide support. This represents the support. These are the crystallites I showed you before. And at temperatures that we're interested in here, the supports themselves, those oxides can actually collapse and occlude the active catalysts, and it's no longer available for reaction. So support collapse is another way in which these catalysts deactivate. A final mechanism by which these deactivate is what's called coke or carbon deposition. And what happens there is that at these substoichiometric oxidizing conditions, some of the fuel is transformed into what's called coke, which is a polynuclear aromatic compound that basically sticks to the catalyst. It's an asphaltene type material that can plug the pores. It can cover up the crystallites as shown here. A blow up, for example, of a crystal here shows how that coke can form on the catalyst, as well as sulfur that can be present in the fuels tends to deactivate the catalyst irreversibly and cumulatively. So all of these are challenges that we have to deal with in developing a catalyst for this specific application. I wanted to show you some specifics about carbon deposition, because this is one of the things that we try to overcome in the catalyst that we looked at. Carbon deposition is what's called a structure-sensitive reaction. That means that the rate at which the carbon is formed depends on the size of the crystallites. So what I've shown here, for example, is a support. These light gray circles might be the catalyst, the active catalyst atoms, and on large crystallites such as this one, the coke tends to form when the biodiesel is oxidized. However, if those particles can remain smaller, the coke tends not to form. So one design criteria, if you will, of the type of catalyst that we want to develop for this process is one in which the clusters are retained in that small structure and they're not allowed to accumulate into crystallites large enough to favor the formation of carbon. So we've learned that the supported metal catalysts are simply not stable at these high temperatures. Carbon formation and sulfur poisoning, I didn't show you that, but it's also a structure-sensitive reaction. And so larger metal clusters of the type that we saw in those earlier slides are simply not going to work. So we have to design a catalyst that allows us to carry out the reaction and retain those active catalyst sites in a stable environment at these temperatures. Okay, so the way that we approached this was to disperse the active metal into the structure to avoid forming clusters. I'll show you exactly what I mean in a moment. But what this was intended to accomplish was to make the catalyst more resistant to carbon. And also, we were able at the same time to develop a catalyst that had these structural defects. It turns out that if we can improve the rate at which oxygen is transported within this catalyst at these temperatures, it minimizes carbon deposition by oxidizing any coke deposits as they form. So that's a very desirable property that we were intentionally trying to put into these materials. This is the material that we ended up with. What I'm going to show you in the next few slides is a result of probably 4 or 5 years worth of effort in looking at how we synthesize, characterize, and develop these catalysts and test them for applications such as biodiesel reforming. This is what's called a pyrochlore. These are not new materials. They are used in thermal barrier coatings and gas turbine blades because they're very, very thermally stable. But their use as catalysts is not widely reported. And despite the fact that they have the ability to withstand these temperatures and the ability to substitute within the lattice catalytically active metals specifically for this reaction. So for example, the empirical formula of the pyrochlore is A2B2O7. These are tetravalent and trivalent metals, as I've shown you here. This is the crystalline structure. The so-called A site, in our case, we looked at a base material called lanthanum zirconate. That means that the A atom is lanthanum, the B atom is zirconium, and into those sites, into the A site and into the B site, by careful synthesis methods, atomic level design, if you will, what we wanted to do was to substitute isomorphically into the pyrochlore structure. At the A site, a little bit of calcium. In the B site, a little bit of rhodium and yttrium. Again, I'm not going to go into the 4 to 5 years worth of work that it took to determine which atoms we wanted to substitute, but just let me say that it was an extremely difficult process to figure out exactly what metals could be put into that structure isomorphically, and exactly how to do that and retain the pyrochlore structure. But that's what we're going to talk about today. A basic lanthanum zirconate material with substitution into the A site and B site with the expressed purpose of trying to improve the oxygen mobility, the thermal stability, and retain the catalytic activity. In this catalyst, the rhodium site is the key. The rhodium is the key to activating the biodiesel. The pyrochlore structure, if we are able to substitute successfully that rhodium into the structure, you can see that it's held in place by these oxygen atoms. The question would be, does it still retain the sort of catalytic activity when it's within the pyrochlore structure that you might expect when it's supported on an oxide in a traditional catalyst? You'll see that the answer is yes, but that wasn't obvious as we began this program. So the catalyst that I've shown you here at the top is the one that we ended up with, again, after much research. What was the exact composition that gave us something close to what we wanted? Remember that we have substituted into the A site, that's where the lanthanum is, a little bit of calcium. Into the B site, which is primarily zirconium, we put a little bit of rhodium, a little bit of yttrium. The minus here means that we also introduced the sort of oxygen-carrying defects that help minimize coke deposition at these temperatures. So this is the LCZRY catalyst that will be referred to in the following slides. We made 2 forms of this. First of all, we made a powder, and I'm going to show you some results on a 50-hour run where we're taking the biodiesel, we're running it for 50 hours, generating a syngas. I'll also show you some results where we've hooked that syngas up to a solid oxide fuel cell and actually run it. However, a powder is not going to be a commercially viable form of this catalyst. We have to develop a way in which that catalyst can be put onto a structured, solid support, much like the automotive converter that's in your car. That converter looks a lot like what's shown down here at the bottom, a monolith with parallel channels. The trick here is to be able to coat that catalyst onto the walls of the monolith and retain the activity. Obviously, with an expensive metal like rhodium, we want to minimize the quantity of the catalyst that has to be used to develop the activity that we want. But again, a long and steep learning curve about how to go about putting the catalyst onto the walls of a structured monolith like this. I'll show you some results in a moment. This is the biodiesel that we looked at. I won't go through all the properties, but we've tested the properties of this material. It was produced from a restaurant vegetable oil. It was esterified at West Virginia State University. And I'll show you, and I think, yes, here in the next slide, the comparison of that particular biodiesel to an ASTM method used to characterize it. Note down here at the bottom that the only spec that we were off on was the total glycerin, and we're quite a bit higher than the allowed maximum there, but that does affect our results a little bit, but we don't believe significantly. But it is a difference between some of the other biodiesels that you might see and the one that we were able to test here. Note that the sulfur concentration was quite low. This is also typical of biodiesel and is in fact one of the advantages of this sort of material. This is an XRD just to show you what the structure of the pyrochlore looks like. These are the diffraction patterns for the pyrochlore at the levels of substitution that we used here. You remember it was 0.11 of rhodium. Even at that somewhat low substitution level, we do see the formation of a small perovskite phase in that catalyst. So it does have some perovskite in addition to the pyrochlore backbone. I want to convince you here for a moment that we actually made a material that does not look like supported rhodium on, for example, silica or alumina. This is a very simple experiment in which we first oxidize the catalyst. Then we take and ramp the temperature of the catalyst in flowing hydrogen and measure the consumption of hydrogen. That's a way of looking at the reducibility of the rhodium. Now, the curve that you see here is for the pyrochlore material. It has a peak at 542 degrees C. If you took that same rhodium and put it on alumina support, it would have a temperature peak around 100 degrees C or even less. So the point I want to make is this is one characterization method that we can use to show that the rhodium is in fact essentially all within that pyrochlore structure. By doing so, remember it's bound by oxygen, so it's much less reducible than rhodium would be if it was in a crystallite on an oxide support. So this and the XRD and other characterization methods that I'm not going to show you here today, including some work done at LSU's synchrotron line, show us that we've in fact achieved the sort of pyrochlorocrystalline structure that we wanted with rhodium substituted into the lattice. This is the results that I promised to show you a moment ago. This is a 50-hour test at partial oxidation conditions. Remember I showed you three conditions: partial oxidation, steam reforming, and autothermal reforming. This is partial oxidation. So here we're feeding the biodiesel with oxygen only and running it for 50 hours. What you'll see there is using the equilibrium values at the conditions that we ran. On the right, you can see that we achieved and maintained equilibrium conversions of the biodiesel on the powder at these conditions for 50 hours. Okay. The next thing that we did was to take that material and attempt to coat it onto the monolith. This was done by a company called Nextech using some proprietary technology. To that catalyst, we added zirconia-doped ceria. The reason for that was that it is an oxygen-conducting material, and the thought was that it not only allowed us to coat that material onto the walls of this a little more uniformly than we might, but it also provided some additional insurance against carbon deposition. So the idea here is that we marry the properties of the rhodium-containing pyrochlore with those of the zirconia-doped ceria to increase the oxygen conductivity. So what I show here on the right is a micrograph of the wall. This is the monolith. This is the square channel walls here. This is the coating here of the pyrochlore and the zirconia-doped ceria. Okay. This is the fuel processor setup. I won't go into a lot of detail, but just to show you and convince you that we actually did run it. This is real. This is the reformer down here. The fuel comes in here, reformed, and then goes into a fuel cell later on. This is a 100-hour run on the biodiesel that I showed you before. Here the reason that there's so much fluctuation here is that the back pressure controller in this larger system didn't work quite as well as we liked. But you'll see on the right-hand side the equilibrium values corresponding to this case. This is an oxygen steam reforming, so we add a little bit of steam, some oxygen, so this corresponds to the near autothermal conditions that I showed you in the earlier slides. And the point here is that at least over this 100 hours, we see no deactivation of the catalyst whatsoever. I've got some runs that I can show you if the question comes up, but we ran for 1,000 hours on an actual diesel that was taken from a pump and saw no deactivation over that long period of time. But on this biodiesel, this is the longest test that we've run to date. And using this particular catalyst, we're able to reach equilibrium conversions for 100 hours. Now, what I'm going to show you next is some tests that we made in which we took this syngas and coupled it directly to a solid oxide fuel cell. We ran at a number of conditions that I'll show you in sequence here. First is hydrogen only. That's just to make sure that the fuel cell is working properly. This is the voltage current density curve. If we run with our syngas with added steam, we get the expected performance, lower than with hydrogen alone, but still what was expected. This is the run with the dry syngas. It's a little bit lower than hydrogen because of the chemical potential of the syngas compared to hydrogen only. This is the syngas with a little bit of steam added. And then finally, a repeat of the first run to show that there is a little bit of deactivation over the course of the test that we ran with the syngas. But the point I want to make here is that we were able to take the biodiesel that I characterized for you, reform it over this catalyst. The catalyst remained stable over 50 to 100 hours, and we were able to operate a fuel cell and produce electricity using the biodiesel as the fuel source. So I hope that I've convinced you that we were able to make a pyrochlore-based catalyst that at least over the time scales that I've showed you was active and did not deactivate. We were able to support it onto monolith. That's very important for any commercial application because that's a form of a catalyst that we'll have to make. I will tell you that we don't believe that's a solved problem yet because we'd like to minimize even further the utilization of the rhodium-containing pyrochlore. It's expensive, as you might imagine, so what we'd like to do is put as thin a coat as we can into that monolith, minimize the rhodium usage, and yet retain the activity that is inherent in that material. So that's work that's still underway. The solid oxide fuel cell performance shows the expected VI response, and we did see some degradation over the timescales that we ran, but it was fairly small. I won't go through each of these acknowledgements one at a time, but I do want to point out the work that was done primarily at the DOE's NETL, National Energy Technology Lab, in Morgantown, West Virginia. My colleagues, Deshant Shekawat, Dave Berry, Dan Haynes, Mark Smith, and Nick Seifert are all located there. I'll call your attention to the second bullet there, which there's a company that was formed called Pyrochem Catalyst Company. It was formed to license this DOE patented technology and commercialize it. It was the first spinoff, I'm told, of an NETL-generated intellectual property, and that company is actively seeking ways to commercialize this. For example, the transportation application that I mentioned earlier at long-haul truck stops, that's one example. The other acknowledgements I'll let you look at, and let me thank Casey again for the opportunity to be here, and I'll be glad to answer any questions.
Yes, front here, please.
I have two questions. Did you compare your catalyst with a regular reforming catalyst? I heard that a regular reforming catalyst, like a nickel catalyst, in the steam reforming can run for like 30,000 hours, which is almost about 3 years. So did you compare with that catalyst? And also the activity of your, what is that called? The loading catalyst. when you apply it to the monolis, did the TOF drop down?
Okay, thank you. Let me answer your first question. The nickel-based catalysts that are used, I assume you're talking about for methane steam reforming. They do last a long time, but that's a completely different situation because it's a different fuel and different conditions. We did use and have looked at nickel as a B-site element. It doesn't work as well. For whatever reason, the nickel deactivates quite rapidly. In answer to your second question about turnover frequency, it's very difficult to measure because measuring the exposed rhodium atoms is not an easy thing to do. Remember, the rhodium is contained as an oxidized form within the pyrochlore structure, and trying to look at the number of surface atoms of rhodium cannot be done with conventional methods that you use to measure turnover frequencies. One of the things that's underway that I didn't talk about today is some computational work at Clemson with Dave Bruce and his group, where they have modeled these pyrochlores, looked at how the surface is truncated, and tried to look at some of the fundamentals of how the rhodium interacts with the other components of the pyrochlore to see how that works, and look at that computationally. I hope that answers your question.
One up front here, and another question here later. There's two there. You can take either one.
I was curious, in the pyrochlore structure, uranium is either +3 or +4, versus in the supported metal catalyst, you have metallic rhodium. So what do you think is the active form when you actually run this pyrochlore? I mean, do you think it reduces on the surface and you have rhodium particles? Or do you really think, as you keep saying, it's surrounded by oxygen, meaning it is in an oxidized form?
I believe it's in an oxidized form, and I'll tell you why. If you run that same TPR experiment that I showed you where I looked at the hydrogen reduction, if you run that repeatedly, in other words, run cycles, do the TPR, make a run, come back, you still see that it's in that oxidized form. Remember, we're running at very, very high temperatures here. The catalysis that's initiated by the rhodium is much more rapid than it would be, of course, at lower temperatures. So the rhodium is not in a metallic form. It turns out that we've run tests where we've attempted to substitute various levels of rhodium into the pyrochlore structure, and you reach a limit very quickly above which the rhodium segregates to the surface in a metallic form, or at least a less oxidized form. When that happens, then you're subject to the same sorts of deactivation that I showed you before, where it can center and the crystallites can move. So there's a limit to the rhodium that can be put into the pyrochlore and maintain that pyrochlore structure.
Okay, but you don't have any actually in situ, let's say, either Zanes or XF's data that actually show you have metallic rhodium? Or do not have metallic rhodium, either way?
We've done Zanes and XFs on our synchrotron line, but not in situ because we can't go to the temperatures that we're interested in. But remember, Zanes and XFs are bulk techniques. So it would be and we're running at very low levels, so you have to use a very bright source of to do anything quantitative, and it's not going to tell you anything surface specific.
There's one other question there, and one last one here. We'll stop with that.
What are the advantages and disadvantages of applying this reforming technology to biodiesel as opposed to conventional diesel or other petroleum products?
I'm not sure there are. It's simply if biodiesel is a given, and it's the source that you want to use for for powering a fuel cell, then the point of this study was to see does that work or not. We have also done a study. I think I've got. This is the study I was talking about earlier. This is pump diesel. So we took diesel from a pump, characterized it, and this is low sulfur. I think it was 7 parts per million. But we ran for 1,000 hours here. The disruption that you see at about 200 hours was when a pump accidentally went off. We were running at oxidative steam reforming conditions. So even though it was unintentional, it stressed the catalyst a little bit more than we might have liked, and actually gave us some good data on how the catalyst could rebound from the loss of steam at these conditions. But this is a test on pump diesel. We did not hook this up to the fuel cell, but simply ran the reformer.
The oxygen content of the fuel, you don't think makes any difference?
I think it makes it easier. I think it's less likely to form coke. I think that the biodiesel is probably an easier application than the pump diesel in that regard.
How do you introduce biodiesel fuel into the fuel reformer? Do you introduce as a liquid, gas, upstream?
It goes through the sort of atomization that you talked about. Perhaps not as efficient, but it's atomized. And I think I may have, that's the reactor system right there that we use for the powders. For the monolith, the test was done in a larger system that I showed you the picture of. That's about a 1-inch diameter monolith. But the powder is tested in the apparatus that I show here, and the liquid is preheated. There's an oven surrounding, you see the reactor, so there's a preheat section. It then goes into a nozzle where it's mixed with air and or steam and atomized at that point.
In the interest of staying with the schedule, we'll stop questions. I'd encourage you to visit with Professor